Hello and welcome back. So, in the previous session, we looked at the very simple 1D test case which we solved in spherical coordinates, and we developed a very simple 1D Poisson or rather a Laplace equation solver in finite elements for this purpose. And now we want to extend this to the 2D case. So first we'll take this test problem, and then there is another test problem for 2D. So in the 2D case, if we try to extend this monopole in infinite domain, the 1D test case that we solved, so we cannot do it directly because in 2D this circle would basically represent an infinite cylinder rather than a sphere. So the actual spherical coordinates solution which we discussed previously, that was constant upon radius kind of solution. So that solution will be applicable for a 3D sphere. So here we have a logarithmic solution. So the solution will be different, but this will allow us to basically understand a lot of 2D related finite element stuff. So the basic stuff which we want to learn, like developing 2D mesh on Gmesh. Then what are triangles, what are quads, how you handle the derivatives, what is the Jacobian of transformation, and what is the mesh quality, what are the parameters we can use to judge our mesh quality. So really we can understand all of these by this simple example, and we'll use the same kind of Robin condition, though in case of a logarithmic solution, it is not so well behaved at infinity, so we cannot just put it to 0 at infinity as we did with the spherical coordinates. But we just want to understand the problem, and so this is basically like an infinite line source, you could say, instead of a point source in an infinite domain. So it will behave differently, but really we are interested in doing just the finite element solution. So let's just solve this, and after this we'll go towards another test problem which we discussed in the introduction, and this involves two circles side by side in an infinite domain, or you could think of them as two line sources again. Infinite line sources. So for this 2D case, we have an analytical solution, and we can map it to the complex plane. So on the right hand side I am showing this image. So on the complex plane you could map it by using conformal mapping, and this becomes a problem in which you just have concentric circles, and you can just solve this. So this is a bit like a coaxial cable problem, you could say, where you're trying to solve for a capacitance. So, and you can solve it and then you can just map it back. So here you could solve it in radial coordinates, and this analytical solution can be mapped back. And so due to this analytical solution, we can easily compute the flux that is leaving this circle and the flux that is getting in to the other circle. So our objective in solving this problem is mainly to do the flux calculation at this boundary. And in finite elements, you must recall the boundary term, which is normal to the boundary, right? And that arises naturally from our weak form after integration by parts. And so this term is present on the RHS, and we can easily use it to calculate the flux at the boundary. Okay, so this is a very easy process, and you just have to extract the RHS and sum it after, which is called as reaction forces. So you do this after actually computing the solution, and you multiply the stiffness matrix without the boundary condition. So we'll have a look at that process in more detail, and you can understand how easy it is to handle boundaries and the secondary kind of important secondary terms, like the flux in the heat flux in the heat diffusion case, or the traction in case of Navier-Stokes equation. So you can handle it very easily at the boundary by using the weak form. So this is the kind of mesh that we'll use for the two circles case. And you can see here that I have used a mesh which is composed of triangles. So the simplest kind of elements which are most commonly used for 2D cases are triangles and quads. And really the mesh and the polynomials, the kind of elements you are using, the kind of noding, so it all depends on the problem that you are solving. So here we are just dealing with a simple Laplace kind of problem. So this is really very isotropic problem. there is no variation in the diffusion coefficient or the constant so the factor that is multiplying the flux is also constant here. So this is a very simple isotropic problem, and so our mesh should also be fairly isotropic, you could say. So let's try to understand first the triangle and quad elements. So let me also show you a quad mesh here. So you can construct it very easily in Gmesh, and I think most of the software started off with triangles because triangles are the most easiest. They are easy to refine and it's easy to build for complex geometries using triangles. And even you could write a simple code yourself in MATLAB for meshing triangles. And so they are the most simplest of the elements and also very cheap to model with or code with. So in this case, actually I will be showing you the shape functions for quads and triangles, and I'll also be giving a shape library for quads and triangles up to the third order. So but I will really be using only triangles for the coding purpose, and really going from triangles to quads is very easy if you have the mesh. So you just have to swap the shape library and you just have to take care of the indexing. So I'll show you how to do that. It's very simple operation. So let's begin first by deriving the shapes. Let's understand what is the triangular shape function and how to derive the polynomials for it. So the process is very similar to the 1D Lagrange polynomials. So these are also triangular Lagrange polynomials. So in the linear case we call them as P1. So if this is your triangle and you have these three nodes, so in the simple linear triangle you just look at the end points of the triangle. So these are your three nodes, and you map it to a linear triangle which is a master triangle, and this is a right angle triangle with an area of half. So this is the psi coordinate, which is like your x coordinate, and this is your eta coordinate, which is analogous to your y coordinate. And so you have this origin, this is your 1 0, and this is your 0 1. And so again we are just looking at two properties: the Kronecker delta property, which means that each polynomial is 1 at one of the nodes and 0 at the other nodes, and you have the partition of unity property, which says that the summation of the polynomials will always yield 1 anywhere inside the element. So the procedure is really simple, similar to our 1D case. So let us define three polynomials here: L1, L2 and L3. So L1, let us approximate it as A1, or rather represent it as A1 psi plus A2 psi plus A3. So you have three unknowns here, so you need three equations, and you can simply solve for it using the Kronecker delta property. So we know that L1 is 1 at the node 0 0, and it is exactly 0 at the other two nodes. So just by solving these three equations, you can get the values of A1, A2 and A3, and you could do the same thing for the other two. And basically you can write a code for this and do this for higher order elements as well. So in case of the linear elements, the solution is very simple. It is like this: L2 is psi and L3 is eta. So you can see that they are satisfying these two properties, Kronecker delta and partition of unity. And so this is a very simple problem, and we can extend this to the quadratics, the same process to quadratics or cubics as well. So in case of a quadratic triangle, you have three extra nodes at the mid edges, and we'll place them exactly at the mid edges because we are dealing with these very simple, so we are not using any complicated elements, simple Lagrange elements, and they will exactly have mid edge nodes. So but complicated elements and very different kinds of elements are available in finite element theory. So we are just interested in more of the multiphysics, which is symmetric, and CFD kind of applications, and for them these kind of shapes are commonly used. And for P3 you would just have two mid-edge nodes, and you would have one node in the middle. So this is your cubic triangle. And for quads, the process for the calculation is exactly the same, but there's an easier hack for this. So in case of quads, this is just a tensor product. So if so in case of quads, your master element looks more like a square. So psi going from 0 to 1 and eta going from 0 to 1. And so the hack is just that for the shape functions for, let us say, q1, which is the linear quad, you just have to take the shape functions for in the x direction or the psi direction, and you take a tensor product with the shape functions in the eta direction. You take linear shape functions in both directions, you just multiply them and get your 4 shapes. So this is the tensor product, so you get exactly your 4 shapes. And when you go to Q2, you will just take quadratic shapes here again in the psi direction, and you will just have 3 nodes here and 3 here. So this will lead to basically 9 nodes total, 3 by 3. So in this case 2 by 2 gave us 4. In quad you will in kind of quadratics you would get 3 by 3 is equal to 9, so you will get 9 nodes. And so the procedure is really the same for all the higher orders. So you could go to Q2, Q3 and so on. So now let's plot these functions in MATLAB, and then we'll have a good idea of how they look. So this is right. So let's begin with quads first. So I have also shown the Gauss points here. So we have already discussed how you do the Gaussian integration. So we did that in the, I have explained it in detail in the previous course actually, but I'll just do a quick recap here. So if you have, let's say you have a 2 Gauss point rule, okay. So let's say I'm trying to find the integral of this kind of function, and I have these 2 Gauss points here. So really what's happening is, let me just draw this again. So if I'm just trying to evaluate this integral, and if there are 2 Gauss points here, so this is like taking a rectangle, and you take the area of this rectangle, and what happens is that this area which is the overshoot and this area which is the undershoot, they just cancel each other exactly. And we do this by actually deriving these 2 Gauss points and the Gauss weights. So you could derive them by a process which is called as the method of I think it's called as the method of unknown coefficients. So I have already shown this in the previous talk, and so this is the idea really. So you just write the unknown coefficients and you solve for 4 equations. So for the 2 Gauss points you solve from x equal to constant to x cube, right? So it can fit up to cubics. So the idea is really, if your Gauss point is equal to 2, then the polynomials that you can fit are 2 into 2 minus 1. So that is 3. If you have Gauss point is equal to 5, you can fit up to polynomials up to 5 into 2 minus 1, that is 9. right? So this is your 5-point Gauss rule, but the idea is the same, that you are strategically placing, so you want the integral under this curve, so you strategically place 2 points here or 5 points, or it depends on the number of Gauss points that you choose, and you just multiply, then you get an area under these, you could think of an area under the rectangle, okay, and so the height is basically the value of your Gauss point, right, this value here, and the width is your Gauss weight. So that's one way of thinking about it. And for the 2D case I have shown this, so it's very simple for the 2D case. And so you are just approximating a rectangle here, and this rectangle is placed strategically such that the overshoot and undershoots just cancel each other. And so this integration is really exact up to the prescribed polynomial order. And in case of 2D functions, we'll have a very similar case, just that we'll have Gauss points, which are just the 2D Gauss points. So in case of quads, they are really similar to the 1D Gauss points, but now you just have x and y coordinates. So so these are your 4 Gauss points at which the actual integral is evaluated, and these are your simple linear Q1 shapes. So you can see that they have a weighting on each of the nodes, right? And so these are the derivatives of those shape functions, right? So derivative along psi and derivative along eta, and so you can see that both the kind of directions are being taken care of, right? All right, so I think there is some error in the representation here, the derivative here. Yes, there is an error in the derivative. So no, I think that is correct. So these are all just the shape functions for your psi, and the eta ones are shown separately. Yeah, that's right. So these are your shape functions with respect to eta. So this is pretty straightforward for your Q1 case. So you can see a variation in both directions because this is a 2D polynomial for Q1, and when you just take a partial derivative, you just see a variation in one direction. It's pretty straightforward. Let's have a look at our Q2 shapes as well. So these are our Q2 shapes, and you can see that they are more curved. And if you look at the edge, then you can clearly see that at the edge they are just inscribing the quadratic shape. Okay, so this quadratic shape is basically at the edge. You can see it's exactly the quadratic 1D Lagrange polynomial which is being inscribed on the edge. And so if you are trying to basically integrate at this edge by using a Robin condition, so you can just integrate it by using 1D quad functions. And so I'm talking about the boundary integral here. So when you are integrating inside the element, you use these shapes which we just saw, right, these shapes. But if I want to integrate inside the boundary, I can just use the Lagrange 1D shape, and this will just match this one. Okay, so I just have to use these 3 nodes. I have to calculate the integral based on the 1D Lagrange polynomial. So if I have used Q2 here, so I just use quadratic 1D shapes. I do the integral, and I can just add them to these nodes. So this is how I can assemble my stiffness matrix. So we have seen this for the 1D case. In the 2D case, this becomes a boundary integral. So in the 1D case, it was just a point integral. In 2D case, we'll have a boundary integral, and we'll have to integrate this line and 1D integral and then add it to the element. In case of 3D, it will be an integral over a 2D face, which will be added to the 3D element, which we'll see. We'll use tetrahedrons in that case. So these were your quad shape functions in up to second order. I have not shown the third order here, but the idea is the same. Let's look at triangles. And triangles I have really plotted up to P3. That is because I think we have a code which will run up to P3. But I mean, really the idea is the same again. But in triangles, it doesn't scale just as symmetrically as it does in, or you could say it is symmetric, but the shape functions are slightly different than in case of chords. So in some of them you will even have piecewise constants, which you did not see in the, so in quads you could see that in the, so let's go to the P1 kind of functions first. Let's just sort them out. So these are your P3. Yeah, so now you can see that in case of triangles they are slightly different. You are getting piecewise constants here. So this wasn't the case for your Q1 element, but this is the case for P1. So this is your P1, and here you are using a 6-point Gauss rule. And I've shown this here because instead of the 2-point, because the 6-point is what we will be using. So this will integrate up to, so there are so many quadrature rules actually. So the one that we are using is a 6-point rule, and this particular rule will work up to polynomials of order 4, and we are not going to go beyond cubic, so this is fine. And these are your Gauss points, and these are your P1 shapes, right? And you can see that when I take a derivative in the x, in the psi and eta direction, you can see that these are piecewise constants. So that is slightly different. So in Q1 elements we saw that we still have a gradation in one of the directions. So P1 is slightly different. So let's close this and go towards P2. So in P2 you can see again that they are curved, more curved. You can see that they have mid-edge nodes now. You have a gradation here from the mid-edge. So you can interpolate better now. You have more number of interpolation points. And you can again see that they are just inscribing a perfect kind of quadratic, right? Quadratic which is going to 0 at these two nodes, right? At 0.5 and 1 it is 0, and at 0 you can see it is 1. So you are again inscribing the same quadratic kind of 1D shape at the edge, and so you can again do the same Robin integration in the same way as I had described for the quads. So right. So let's move ahead and let's look at the derivatives. So now you can see that the derivatives are really having strong curves, like rather in this case there isn't a curvature, but you can see there is a straight shape, but it's having a strong slope, a really sharp slope. That is because you are having really sharp curvatures in your actual elements, and you are again seeing some piecewise constants here. So those are your P2 shapes, and in case of P3 shapes you can see even more curvatures. So these will be obviously good for handling your smooth functions, but they will struggle when you try to approximate discontinuities, right? So you have two mid-edge nodes here, and so you can see that this is inscribing the cubic. It is 0 here, here, and here, and it is 1 here. Okay. So again you can use the same. So it's the same logic. It's just P3, and you can see that the P3 derivatives are even more sharper because the curves are also sharper. So they have a strong slope. You can see that the values are pretty high, but it is fundamentally different than your quad kind of shape, right? So at least it appears pretty different. Okay, so these are your P1, P2 and P3 shapes. So now we have taken a look at the shapes. So now let's think of how to model those derivatives inside those shapes. So in the 1D case, this was very simple, mapping x to psi. We just used the chain rule, right? And so this was very simple, and basically you can think of dx by dxi as basically the ratio of your physical to your master element. And so even when we did the integration, we just multiplied by this ratio so that this would scale the integrand correctly. So now we have to do this in 2D, and this is slightly more complex, so we cannot just do a single operation. So let's see how to do this. So psi is your shape function inside this triangle, and we are interested in d psi by d psi. So these are the partial derivatives, and these are your partial derivatives of the 2D psi shape function in the eta direction. And since the polynomial is curved in both directions, as we have already seen on those surface plots, really you have to take the derivative, you have to apply the chain rule in both directions, right? So you are getting these kind of two terms here, and we can just take these yellow or these orange terms out, and get this nice matrix of this green these green terms, and this is what we call as the J, or the Jacobian of transformation. And so this is a very important matrix even from a point of view of the mesh analysis. And to compute this matrix, we simply have to do the summation and the interpolation like we did before, the isoparametric mapping. So simply you get these x values from these three nodes in your physical element, and d psi by d psi are coming from your shape function library. So you can just add them and you can get this Jacobian matrix. And to get your physical derivatives, you simply take the inverse, because you might have seen, so you just have to take the inverse of this matrix to get your d psi by d psi. I'm sorry, d psi by dx and d psi by dy. Okay, so this is your so this is how you compute your derivative. And for the integration, you can see that the area, so here we are not dealing with the length but the area. So dx into dy, you could think of it as the area, and this is d psi, d eta is the area of this triangle. And so you can just multiply by the determinant, and this basically scales your area or the integration correctly. And we have to remember that there is a 0.5 factor involved here, because the area of this triangle is basically 0.5. So we just have to remember that in our computations. In case of quads, the area is 1, and typically when you use Gauss weights, you have a factor multiplying those Gauss weights. So in case of triangles, you can just multiply it by 0.5. And then you would get the accurate flux values at the boundaries. Otherwise, you would just get the twice the same values. So this is basically our shape functions and how to compute the derivatives. And now we are in the position where we can just move ahead and start some meshing. And let's also look at how this J factor, which is basically just you could think of it as a ratio which is scaling the areas of both of these triangles. How does this factor into the mesh quality as well? So let's just move to that now.